We've already learned that the modern inhaled anesthetics differ from the anesthetics that preceded them by the addition of, what was it? The addition of what? Fluorine. Fluorine. You've got to raise your hand and say fluorine loudly. All right. And that changes the physical properties of these compounds. And it's best illustrated in a comparison of two of the modern inhaled anesthetics, which differ only because they have a fluorine substituted for another halogen, which is the chlorine. What are those two anesthetics? What are they?
Isoflurane and desflurane.
Isoflurane and desflurane. Let's look at that. The formula for isoflurane, what is it, Michael?
It's a carbon, an oxygen, and another carbon.
And another carbon. And then we got to fill in all the details. And where are the details?
In the alpha ethyl group, I think there's a chloride there.
There's a chlorine right there. Okay, what else?
And I believe that there's one more chloride, or a fluorine somewhere.
There's fluorine, lots of fluorines. There are 5 fluorines that you got to distribute.
Oh, it's a hydrogen.
Okay, that's right. And then there's another hydrogen over here.
And then the rest filled in by fluorine.
The rest are filled in by fluorine. And what compound is this?
Isoflurane.
That's isoflurane. And how do we change that to desflurane?
Chlorine and
Louder.
Take off the chlorine and put on a fluorine.
Take off the chlorine and put on a fluorine. That's the only difference between isoflurane and desflurane. And what does that do? What does that do to the physical properties? The lady with the hand raised here. Tell me.
It increases the vapor pressure.
It increases vapor pressure. So vapor pressure goes up. And we've had a little illustration of that. Along with the vapor pressure, of course, the boiling point goes what?
Down.
Goes down. All right. And we got an illustration of that, which we'll see on this plasma screen. So we've got sevoflurane, and we've got suprane. And that's Quinn's hand. And Quinn is, I think it was Quinn, wasn't it? Injecting some sevoflurane, just injecting right on the tabletop there. And now he's injecting some desflurane. And watch the difference between these two. Here's the outline of the sevoflurane. And you can see the outline of the desflurane already beginning to shrink. And this will disappear long before this liquid disappears. Doing so because its vapor pressure is much higher, so it evaporates quicker, and its boiling point is much lower. What's its boiling point? What's its boiling point? Yes, sir.
I believe it's 22.5 degrees Celsius.
Yeah. Of course, its boiling point will depend on the barometric pressure, so we're assuming 1 atmospheric pressure. Now, what else changes? We know the vapor pressure and the boiling point change. What else changes when we add some fluorine?
It's less biodegradable.
It's less biodegradable. It's more resistant to degradation, so it's more stable. And maybe less toxic because of that. And we'll get into that in our discussions of hepatotoxicity and nephrotoxicity. Anything else? Any change in the physical characteristics?
Solubility decreases.
Solubility decreases. That was the whole point of this. That was why we changed from chlorine to fluorine. So solubility goes down. Good answer. Anything else? Yes?
Potency decreases.
And potency decreases. So MAC goes up. Not quite a physical characteristic, although clearly how anesthetics work is going to depend in some degree on physical characteristics. Now let's talk about one of these issues here, the issue of stability and toxicity. The stability of the fluorinated anesthetics is greater in the presence of absorbance absorbents such as the ones that remove carbon dioxide from the gases our patients breathe. This is from a study that we did in which we simply put 100 grams of soda lime in a bottle that had a 600 ml capacity, and we added some anesthetics. And then we noted how much of the anesthetics degraded in each hour. And we found in a comparison of these two anesthetics, isoflurane and desflurane, that desflurane was more stable. That goes along with what we said, with the greater stability of the fluorine carbon bond than the chlorine carbon bond. So the absorbents at higher temperatures, like 80 degrees, and although you can't see it at 60 degrees, were more apt to break down something like isoflurane than break down something like desflurane. But the carbon-fluorine bond does not make for invincibility. As you can see, sevoflurane, which is only halogenated with fluorine, is degraded by soda lime, and degraded to an appreciable extent at higher temperatures. Are these temperatures reasonable temperatures in which to study the degradation of something like sevoflurane? Or no, because that isn't the temperature in the operating room, is it? Quinn is shaking his head. So the temperature in the operating room is going to be what? What's the temperature in the operating room here at Wake Forest?
28 degrees.
28 degrees.
27.
Do I hear 26? Do I hear 25? No, it's less than that. 28 degrees would be pretty warm. And the surgeons would object, even though we find it very comfortable. No, more like 20 to 22 degrees. And so Quinn's objecting. He says, look, that's 40 degrees. On the other hand, in a closed circuit anesthesia system, what's the temperature in the absorbent?
40 to 60.
40 to 60. Why is it hotter than the room?
Exhale gas.
Why is it hotter in the room? You got to raise your hand.
You have exothermic reactions going on between the or the soda lime and the absorbent and the carbon dioxide.
Yeah, you have an exothermic reaction. So it creates heat. And this is indeed a reasonable temperature range to consider the degradation of inhaled anesthetics. So that's why it was done, in fact. Now, the degradation by soda lime is caused by what component of the soda lime? What component of the soda lime? We got Tracy here who's going to answer that question.
The base is either sodium hydroxide or potassium hydroxide.
Now, are those the only bases in soda lime?
No, there are other bases, but
What's
the
the other
monovalent.
base?
What's the other base?
What's the other base? You only got a certain number of bases. You could have lithium hydroxide. Is it lithium hydroxide? Nah. What other base could it be? You've got divalent bases. What are they? What are the divalent bases? You got a hand back there. Someone wanted to help you.
Barium hydroxide?
Barium hydroxide is one, but that's not what's in soda lime. What's the other divalent base? Got an answer here.
Calcium?
Calcium hydroxide. That's the other base. But it's the monovalent bases that do most of the degradation. The sodium hydroxide and the potassium hydroxide that do most of the degradation. So we could eliminate the degradation or markedly reduce it if we got rid of those. And that's what's been done in a new absorbent called Amsorb. So Amsorb doesn't contain any sodium hydroxide or potassium hydroxide. And Amsorb does not degrade the anesthetics. Wouldn't do what I showed you in the picture that you saw a moment ago. What are the degradation products that we find from the modern inhaled anesthetics, particularly anesthetics like isoflurane, like desflurane, and like sevoflurane? What comes from these anesthetics? We got an answer from Quinn here.
Carbon monoxide.
Carbon
the worst.
monoxide. From which of the anesthetics?
Mainly desflurane and isoflurane.
From
And
desflurane
enflurane.
And enflurane, that's right. And what comes from sevoflurane?
Compound A is the
Compound
worst.
A
Yeah.
is really the only one that's of concern to us. Now we got to consider that absorbents aren't always the same. The absorbent that you see in there may be different one day from another day. It may be moist one day and it may be dry another day. In fact, how much moisture is in soda lime and barrel lime? How much moisture?
15%?
15%. Is that by weight? Yeah.
Yes.
Yeah, by weight. So we've got 15% water. So you buy that soda lime or the barrel lime and you get water. And that's important. It's important because, first of all, it can accelerate the reaction with carbon dioxide. But second of all, it protects against the degradation of the inhaled anesthetics. And it protects against the degradation of all of these. So with desflurane and isoflurane, if you've got normal absorbent, moist absorbent, you have no production of carbon monoxide. It's only when the absorbent is dry, and that in fact is drying by 90% or more, that you get carbon monoxide production. You get compound A production, however, from both moist and from dry absorbents. How can we get drying of the absorbent? How can that be? It's sitting in that closed container. Let's see, who haven't we called on? Gentleman with the orange tie.
Well, you get drying of the absorbent if you have high gas flow rates. Touch the absorbent for an extended period of time.
Right, right. So if you give an anesthetic, and at the end of the anesthetic you turn off the oxygen, there's no problem. But if you leave it on and you go away for the weekend, there may be a problem. What else do you have to do besides leave the flow on in order to get drying?
Well, there has to be actually contact with the absorbent by the flow. So it's nice to have a reservoir bag or something on to perhaps deflect that flow.
That's right. So if you've got the reservoir bag on, even though you've got a high flow that you leave on all weekend, no problem. And that's because here's our circuit. Here's the gas flow coming in. And there are one-way valves. And here's our reservoir bag over here. And here's our absorbent here. The only way this gas can go back through here is if there's an opening here. Someone took the reservoir bag off and the gas can come out here. That's the only way you can get drying. Leave the flow on and remove the reservoir bag. Then you can get drying. And then you can get the production of carbon monoxide. What is compound A?
Vinyl ether?
It's a vinyl ether. So you take sevoflurane, we've been drawing isoflurane there. Take sevoflurane, which is this compound. And have that react with an absorbent. It removes one fluorine and this hydrogen. And the result is CF2 and a double bond here, and that disappears. And that's compound A. A highly reactive compound that will spontaneously react with proteins in the body. So if you mix compound A with blood, it disappears in a matter of minutes. It disappears because it irrevocably binds to the proteins in blood. Now, what's the concern about compound A? Is it blood proteins? No. I've got a shaking head over here. It's not. Well, what is the issue then?
I thought the issue was you worry about liver toxicity, and you can also worry about some about the kidneys, but in the reading...
Who would vote more for kidneys than liver? We got a group voting more for kidneys. Yeah, the kidneys are the ones that are thought to be attacked. What is the evidence that indicates that compound A causes renal injury in animals and humans? What's the evidence? Jane?
Well, in rats, there's evidence there, you'll have proteinuria, enzymuria, and renal tubular damage.
So you got necrosis, proteinuria, and enzymuria. Well, what about humans?
In humans, you get you also have enzymuria, glucoseuria, and I believe proteinuria as well.
But not necrosis?
I'm not sure.
You're not sure because it's never been studied. So no one can possibly know. And that's right. The people who argue that humans are not damaged say, look, there's never been evidence of necrosis. And these are kind of esoteric markers of injury. But it is interesting that there are these parallels, that there are these markers of injury that correlate with necrosis in rats, and they are the same markers that appear in humans. We'll come back to this and discuss why this is in fact a minimal problem or no problem at all for most of the anesthetics that are given with sevoflurane. Now, despite the fact that this is a minimal problem, we have to take it into account because the package label tells us that we have to take it into account. What does the package label say to us? What does a package label say to us? Yes, back here.
You can use 1 liter flows for up to 2 MAC hours, and then after that you end up having to increase your flows up, I think, to 2 liters.
Right. So it says don't use sevoflurane at flow rates less than 1 liter per minute. And if you're going to use 1 liter per minute flow rate, don't use it for more than 2 MAC hours. So, and that's to take into account this potential of compound A to produce renal injury. Why did they put that warning in there? I mean, how does that help you? Why is a low flow rate a concern?
Just because of the buildup of the compound A, and you want to kind of increase your flow rates to hopefully eliminate that.
To wash it out.
Correct.
So it will wash it out better. But in fact, there are other reasons, aren't there? What are the other reasons why it's important not to have a low flow rate for a long time?
Basically, with a decreased flow rate, you can have an increased temperature in your absorbent and
Right.
basically increase the production of compound A just
Exactly
by
so.
low flows.
Exactly right. So Jennifer and I, in fact, talked about in the operating room. We're giving 6 liters of flow, fresh gas flow, into the system, 2 liters of oxygen and 4 liters of nitrous oxide, along with our sevoflurane. Is there any danger under these circumstances that there could be renal injury from compound A?
No, I would think with such high gas flows that none of the gas is actually being rebreathed, that we shouldn't have any problems with compound A production.
Okay, let's lower those flow rates to 1 and 2 liters per minute. Now it's a total of 3 liters per minute. Do we have any rebreathing now?
You have partial rebreathing.
Partial rebreathing. Is there any risk from compound A under these circumstances?
No, I would think that the levels of compound A that are actually being produced are still fairly low, that you won't see actually any renal injury.
Okay, and why are the levels low?
Because you have your high gas flows.
And what does that do to the carbon dioxide that gets to the absorbent?
Basically, it's decreasing the amount of carbon dioxide that actually gets to the absorbent, which helps. And a decreased amount of carbon dioxide decreases the temperature of the absorbent, which also decreases compound A production.
So the temperature just doesn't get very high
Right.
in the absorbent at this flow rate.
Right.
All right, now let's go down to a lower flow rate. Let's go down to 500 cc's of nitrous oxide and 500 cc's of oxygen. Now, do we have partial rebreathing now?
Yes.
Again, we have partial rebreathing. Now, is there any risk from compound A?
I would think it'd be minimal if your procedure was under 2 MAC hours for
Is that what the
sevoflurane.
package label says?
Yes.
We're allowed to do this. Is that right?
Yes.
But what happens if we go beyond 2 MAC
You
hours?
need to increase the flow to 2 liters per minute
This is a higher risk. Why?
because you have a higher production of compound A.
Okay. And more rebreathing of that compound A. Why don't you lower the flow rate to 300 and 300? So now our total flow is 600 cc's per minute. Is this permittable?
No. The minimum flow is 1 liter per minute.
So
with
we shouldn't go
sevoflurane.
below that
Right.
1 liter per minute flow rate.
Right.
That covers what we need to do in terms of keeping safe and avoiding any problems with compound A. Let's go back to the issue of drying of the absorbent and ask how can we ensure that the absorbent doesn't dry so we don't have an issue with carbon monoxide? What do we have to do either to prevent or manage absorbent that has dried? What do we have to do?
I think you should check your canister on a regular basis. There's indicators in the canister that determines if actually the canister is dry.
What indicators are you familiar with that do that?
I don't know off the top of my head. I would think like I don't know.
That's a good answer. It's always a good answer. In fact, there aren't any presently, although there have been suggestions that we would like to have such that would tell us when the absorbent is dry. So we really can't tell. We can tell when the absorbent is exhausted by the change in color, but that's a different phenomenon. So what are we going to do to ensure that the absorbent is not dry? Michael?
Well, we can start out, of course, what we were talking about before is making sure that we don't have high flows going through the system when it's not in use. Second of all, a lot of times there is a kind of an indicator that you can use. You can see condensation formed around the inside of the canister there.
Where the absorption has taken place. But that can be misleading. Why is that potentially misleading? Can you make water by putting carbon dioxide into an absorbent?
Yes.
That's one of the outcomes of the interaction of the carbon dioxide with the absorbent. So it might be misleading. The absorbent might be dry. But that's a reasonable thing to suggest. It's reasonable to think about that. So if you always kept a low flow rate, that would be one way of preventing drying from ever occurring. What are you going to do if drying does occur, or you suspect it occurs? How are you going to manage that? What are you going to do? Go ahead.
You can always just add water to the absorbent.
Just add water. Just add water. And what else can you do?
Replace it.
You can replace it. Yeah, you just replace it with stuff that's right. Now we've got an illustration of the replacement of We've already learned that the modern inhaled anesthetic by pouring water into the absorbent. Which absorber is the important one? The top one or the bottom one? We got to vote. I'm going to take a vote here. Who votes for the bottom? Nobody. Who votes for the top? Oh, no, it's wrong. It's the bottom one. See that? Just pour water in. Or as some wag said, when you go out for coffee, get 2 cups. Drink one and pour the other one in the absorbent. That'll work fine, too, and adds a nice smell to the question.
In Grand Rounds this year, we had a discussion on pouring water into the absorber, and our institution, they said not to do that. If you had any concern about it, pretty much take off, if not both, then the lower canister.
Right.
And I'm not.
And replace it with fresh. And that always
because even the insert says, does the insert on the absorber say that you can pour water into it?
I don't know. But I know you can. And I know that there's been at least one study that suggests that works, that you will rehydrate the absorbent simply by pouring water into it. Which anesthetic can spontaneously degrade? Right in the bottle. You're going to tell us. Sevoflurane can spontaneously degrade. Under what circumstances might it degrade?
I think initially they had to change the bottle itself because of the component of the bottle.
That's right. So one of the components of the bottle, particularly the aluminum in the bottle, can catalyze the spontaneous degradation of sevoflurane under one other circumstance. What's the other circumstance that you've got to have?
Exposure to light.
I'm sorry? Go ahead.
Exposure to light.
No, although that's always a concern. Ultraviolet rays can cause degradation of many anesthetics. But what other condition? Anyone know?
You need water.
Say it again.
You need water.
You need water to do what?
It preserves the anesthetic.
So the dry condition is what predisposes. And indeed, the manufacturer of sevoflurane has now remedied this by putting water in the bottle and by producing a plastic liner for the bottle. So this issue of spontaneous degradation no longer is an issue. And the issue, I think, was of potentially great importance because the degradation was to highly acidic, volatile compounds like hydrogen fluoride or silicon tetrafluoride, which can rot the lungs. So we didn't want that. But they have now dealt with that problem. That problem no longer exists as a factor. Can inhaled anesthetics hurt the environment? Tell me about it. I see a nodding head here. You said it.
Yes, they can, just because when they're released into the atmosphere, they're breakdown products, because I think for every one of chlorine atom that is released, it goes and helps destruct the ozone layer, essentially.
Right, right. So chlorine is of concern to us. The chlorinated hydrocarbons are of concern to us. Which of the anesthetics that we deal with is chlorinated?
Isoflurane.
Isoflurane. That's the only one. Sevoflurane and desflurane don't have any chlorines on them. No chlorines at all. So they are not an issue as far as the ozone layer is concerned. What's the other concern as far as the environment is concerned?
I believe nitrous oxide contributes to the greenhouse effect.
Exactly so, just like carbon dioxide does. Is that a big problem for anesthesia? Do we contribute a lot?
Probably not very much. I'm certain that nature contributes more than we do.
And where does nature contribute? Where does it come from?
Like volcanic eruptions, I believe.
I don't know what's in volcanic eruptions. It's possible. It's possible. All right, well, I want you to note that we aren't polluting this sky. This is the sky over Wake Forest, and it is clearly the bluest of skies anywhere in the world, and we are not affecting that by our delivery of anesthesia. Are there occupational exposures that are of concern to us? You think there are?
It's thought that nitrous oxide could possibly be able to cause abortions in high enough levels, but usually in the amounts that you receive in the operating room environment, it's thought to be negligible.
Why is it so low in the operating room environment?
Well, we have a scavenger system in our anesthesia machine that usually sucks out all the waste gases and will pump them out into the environment. So it's not you're not actually getting exposure in the operating room, but
you expose the rest of the world.
You expose the rest of the world. That's right.
Okay. And for what other reason is exposure in dental operatories, or in regular operatories, minimal?
The air turnover in the room.
The air turnover in the room is high. How high is it? How many turnovers are there per hour by law in many states at least?
I do not know. Isn't it 7 to 8 an hour?
At a minimum. In fact, 10 to 15 is the usual number of air turnovers per hour. So you'd have to really have a high flow in order to contaminate an operating room. But where might this be a problem? Where could it be a problem? Not in regular operating rooms, but where else is nitrous oxide used? Where else is it used?
In dental offices.
In dental offices. And then there's a new practice of anesthesia, a new practice that's going on and is increasing at a rapid rate. What practice is that?
Office-based anesthesia.
Office-based anesthesia. And it may be there that you're going to get contamination of the environment, and you may have this problem of occupational exposure that may induce abortions. So that's a concern to us. What are the NIOSH limits that we want to think about, although it's never been proven that exceeding these limits produces harm? What are the limits?
I believe it's 2 parts per million and nitrous 25 parts per million.
So 2 parts per million for the potent inhaled agents and 25 parts per million for nitrous oxide. There are variations on this that we could talk about, but in fact we easily get under those in most of the cases that we do. Okay, there was a question.
What about the effect of inhalation of nitrous oxide by providers and the effect on B12 metabolism and neurologic deficits?
That's a whole story of it in itself. As far as I know, there are few, if any, effects of occupational exposure to nitrous oxide that involve the inactivation of methionine synthase, which is what you were talking about, the inactivation of the vitamin B12 moiety that's in methionine synthase. Methionine synthase is an important enzyme. Methionine synthase catalyzes the reaction of homocysteine and tetrahydrofolate to folic, folinic acid, and methionine. That is the creation of an essential amino acid and a component for the construction of DNA. And it's been known that nitrous oxide, given at high concentrations for prolonged periods of time, for example, to tetanus patients, to decrease the pain from spasms of muscle, given for days, can produce an aplastic anemia and death. And that's the mechanism that's thought to underlie the injury from nitrous oxide. But we don't give nitrous oxide for a long enough period of time to patients to create that state. And because we breathe such low concentrations in the operating room, we don't get exposure to nitrous oxide that will do that. There may be certain patients that are at particularly high risk from injury from nitrous oxide. Patients with vitamin B12 deficiency, so patients with pernicious anemia, for example, may be at risk from this effect of nitrous oxide, where ordinary patients are not. Patients who are real vegetarians and don't get any vitamin B12 may be at risk. But ordinarily, this is really not an issue. Any other questions before we go on to Mac?
Question about the degradation issue with the volatile anesthetics. If it is an issue at all, why don't they use absorbents that don't have potassium and sodium hydroxide in them and eliminate that?
That's a very good question. Why don't we do it? Just get rid of the problem. Everybody buy Amsorb. Well, there are several problems. We have to talk to Dr. Roy about this because one of the problems is cost. The new absorbents command a premium, and it's very high. Not only is it very high, but their absorbent capacity, as far as carbon dioxide is concerned, is perhaps half that of regular soda lime. So not only do you pay more, you get less for your money. There's another reason, which is that there isn't much profit in absorbents. And the companies that make absorbents are loath to change because they have to prove to the FDA that when they've made the change, they've gotten rid of the monovalent bases, they haven't changed the safety or characteristics of the absorbent. They have to do studies. And if you're talking about something that makes a profit of maybe a few $1 million a year, it isn't worthwhile. So that's the basic answer, forgive the pun. One more question.
When did the manufacturers of sevoflurane add water to it? And did that seem to affect the apparent potency of sevoflurane?
They did that fairly recently. I believe in the past year they added the water. It does not alter the potency because the amount of water that's added is very small. You need very little in order to prevent this degradation from occurring. So that it doesn't alter the physical characteristics of sevoflurane at all.